Okay, hi. In this video, I'm going to talk about the Collazt conjecture proof. So the Collazt conjecture, here's a brief summary of what Collazt conjecture say. So the Collazt conjecture say that if you have a function g of ni, so that g of ni is equal to 3 of ni plus 1 over 2 to the k. So that g of ni is r, and ni is r, when ni is r. And when ni is even, then you do this ni over 2. Actually, this statement also includes in the first one, because you have k is, so that g ni is r. So just ignore this one. So the Collazt conjecture states that if you have this equation here, and then you substitute recursively, you will get a cycle of 1, 4, 2, 1, 4, 2. So the domain of the function is g. The domain that we are looking at is g is x, so that and x belong to all natural number different from 0. Same for y, for all natural number different from 0. So the range of the, so we need to find, as the beginning we see the cycle, so we're just gonna set the set of cycle equations to see what happens. So we set n g of n0 equal to n1, g of n1 is equal to n2, g of dot 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 to all the way to g of n minus 1 equal to n, and g of n is equal to 0. You see the cycle, and if you keep doing the g of n0, you get n1, and then it's the cycle. One more thing, if the function is defined in the domain, and if there is a cycle, then all of the elements in the domain must obey the cycle, must be in the cycle. Okay, so now I substitute g of n1, now substitute n1 into here, or g of no into here, and all the way to n times, so we get g of g n times of n0 equal to n0. So now I just substitute this in all the way, substitute the function into itself, and I see that k, at first k must be bigger than 1, because the first thing here is must be bigger or equal to 1, because here 3n plus 1 is an even number for sure. So from here I can just write 3 n times. In here we substitute it 3 times, so we get 3 n times, right? And n0 we just ignore, we just put it in the side for a second. First we separate this thing out, separate this thing into the two, and then multiply it in. And since we have k1 plus k1, k2, k3 is always bigger or equal to 1, so now we can just write k1 plus k2 plus k3 plus k4 all the way to kn minus n to the power of n, which is the same thing. So from here we can see that the less outside of 1 over 2 to the k, the less power it will have, and the more it go inside, the more power it will have, right? So, and also 3 here, in here we have one less of 3 already. We just have 1, 2, so the power will be n minus 1. So here we get this, so based on that we get this expression of 3 over 2 to the k1 plus k2 plus kn minus n to the n power, plus for summation of I go to from 1 to negative 1 to n minus 1. As I said before, this thing must be n minus 1, and this thing uh, is the more it go out inside, the less power it will have, and this thing is the same thing as we said. So now we see something in common. We see we see that this 2 to the k1 plus k2 plus k3 plus k4 all the way to kn and minus n is in common. So we just go 2 to the n as general here. It's not equivalent, but the probability will be the same, because it's the same power for each here, for each power here. So we just want to make it shorter and easy to work with. So here we get this expression here. We substitute 2 to the k, yeah, and we said, as we said before, we said g of n is equal to n0. So this expression is equal to n0. So 3 over 2 to the n power time for n0 plus for this expression. Actually, it's this expression, but I do some algebraic manipulation. I get this thing and this thing out, because the top and the top can cancel, and we left with this and set up into n0. And also this can be written as 3 to the I over 2 to the 1 plus for I, and 1 to the 1 plus for I left 1 half out, and then I left with this. And this actually trigonometric series, and we get with this expression for the value of this thing, and do some manipulation. I get this expression right here, which you can try to do it. It's simple. It's just algebra. And now do plus 1 in both sides, and then I get this thing. I can cancel this out, and the reason is NO is a natural number and bigger than 0. So there will be guarantee that this value will not be 0. So I cross it out, and I left with this. What we realize is that if the case before, when we didn't call this as 2 to the n, then at this point it will be 3 over 2 to the k1 plus k2 plus k3 all the way to kn minus 4n parentheses to the power of n equal to 1, and to the power is equal to 1, so n anyhow n must be 0. So what can we say about n equal to 0? So there will be only cycle where the length is 1 odd, and that odd must be 0. It must be n0. Now we just need to find the cycle that is created by that odd number, which could be 3, 5, 7. We didn't know that yet. So now we calculate, we try to find that value. So the length of the cycle is 1, so we are just gonna set g of n0 equal to n1, and g of n1 is equal to n0, right? So now from here we can just substitute this into this, or g of n 0. So we get this expression, and separate and solve for n0, because we have n0 in both sides. So for one side we get this expression. As we said before, the domain of NO must be positive real number, positive natural number. So positive natural number, right? So this expression, this thing have to be bigger than this thing, and this thing have to be divided by this thing. Since this thing divided by this thing, you have to do modular arithmetic, and which I'm not gonna do it because it's complex. I'm gonna do something simpler. I'm gonna get this bigger than this, so this thing is divisible by this thing, so here I get this expression here, and this thing is bigger than this thing. I'm just gonna solve for this, and if we have restriction, and then if we have restriction, we can just plug it in to check if this expression is true. If it's not, then we eliminate it. So that is easier to work more than modular arithmetic. So now I put it all in one side, and then put 2 to the k out, and I get left with this. So now we see something that is quite beautiful. I mean, yeah, quite easy to work with. So we left with this equation here, and we know that k and k1 must be natural number also, bigger than 0, of course. So k1 max is 3, because if k1 is 4, then this will be negative 15. Negative 15 times for 2 to the k, which is always negative number that's bigger than this, so it's never gonna bigger than 0. So 3 is max, and at that point k can be either 1 or 0. Now we transfer the infinite calculation as the question asks to the finite calculation. So now we do the table to calculate when k1 and k work. So k1 here, when k is equal to 0, 2, 1, and 2, and 3. k1 is 1, 2, and 3. Here's my calculation. You can do calculation on your own, because I'm not gonna work through all the calculation. You can tap in calculator or calculation computer or whatever. Now we left with just only one candidate that is satisfied, because all the candidate is negative number and ratio that have the denominator different from 1. In fact, if we extend the domain and the range of the function, you will somehow get the cycle at this point. Try it, and you will see. Actually, it's more than this thing. It's more than this table. If we extend the domain. Now we just need to test if the first condition is true, as I said before. So as I said, we see the first condition is this condition here is true. Then we just have one candidate, so we left but when k1 is equal to 2 and k2 equal to 2, and we sub it in here, which is the first expression, and we get 7 divided by 7 is divisible by 7, which is true. So the Collazt conjecture must be true. Thank you.